This theorem, right? Yeah, there was a second part which says that, well, with typos. Now you're going to see the second part without typos on my dynamic slides. Look at this. Oh, well, actually, I opened the Wikipedia for nothing because I have here the definition of the limit. I have typed in here. You see, it's another. I didn't realize I have it typed on the slide. So, like I said, I opened the Wikipedia for nothing. That's the same definition, exactly the definition of the limit, and that's how it looks. Okay, let's just look at the corollary. Look what it says. It says that if you compute the d-limit of a sequence, meaning that Euclidean metric, this is the same as if you compute the dp limit of that sequence with respect to the dp metric. Everything is correctly typed now. That's the correct statement of the second part of the theorem on my slides. And that is true for every p. 1, 2, 3, including infinity p. Well, of course, normally you can't write number equal infinity, but I hope you understand what I mean. I mean that if you take the infinity metric in here. I just look at the proof. It's a very simple application of this theorem. Look at this. I take the left-hand side in this equivalence, and I say, by the first part, this is equivalent to, if I restate this in terms of the metric sequence, in terms of this AN sequence, that's how it will be. It's a numerical limit. I need to scroll it up a little bit. Now, if I use my previous theorem about this equivalence of matrices, or of metrics, sorry, I can say that I have the following relation between the metrics. Euclidean metric, obviously it's non-zero, it's a positive definite. It doesn't exceed p metric with this factor. That's something we proved with you on my previous, in the previous theorem. And then the p metric itself doesn't exceed Euclidean metric. Remember, Euclidean is a d2 with another factor. Here's another factor, and how, and root. So I use this corollary second part of the theorem on my slide, in the previous twice. First here, with the index q here. Remember, in that term, there's a q here. This time q is number 2. That's why it's 1/2. And then p played the role of q again, and that's why we have extra 1 on p. So if you are in a position to write something like this in the assignment, you have to make a proper reference to this equivalence between the dp metrics theorem, twice used in this multiple inequalities. Okay, I keep on. Now I can say, what I can say? Oh, look at this. If my Euclidean metric, or if this sequence goes to 0, by something which you called in the first year sandwich principle, you can say, look at this. My p matrix squeezed between the d metric and the d metric on both sides. And there's a typo here. Yeah, do you see the typo? It's a typo. I'll show you where the typo is. You see? It's just a little bit. You see, originally when I said my sequence, I used n for the index of a sequence and m for the dimension, m for Mary. Well, if in that theorem, which compares the metrics, the equivalence theorem, the n factor there, which was there, it was the dimension. It had nothing to do with the index of a sequence. There wasn't any sequences there at all. So that's the typo. This here is supposed to be m, not n. Dimension. If it was n, then we couldn't use the sandwich principle because the factor was growing with the index, but it's not the case. M here is a fixed dimension. We're not altering the dimensions. We're not jumping from space to we're not jumping from space to space. That's how it's supposed to be correctly typed. And now I can use the sandwich principle because my dp number squeezed between the two vanishing sequences with some factors, but the factors are independent. It's just a constant. And that's why I can say that the limit in d of dp sequence is also 0. But now if I use my theorem again, this equivalence, in the reverse direction, then this is equivalent to dp limit of a sequence. And here we go. Look at this. I started with the assumption that my xn converges in the Euclidean metric, and I concluded that the xn converges also in the P metric. The key ingredient in the whole argument was this equivalence between this inequality, which allowed me to use the sandwich principle. Yeah, and that's the end of it. I think you can. I don't think I have the opposite direction. So we prove the inequality this way, right? We prove this direction just now. For the opposite direction, you have to. We can use the opposite actually. We can actually use the one right straight away, because if you start from this side, then you make a step here. Limit of GPs go to 0. Then your Euclidean metric squeezed between the number 0 and the vanishing sequence. So G numbers also go to 0, and you come back. So actually, it's easily reversible, the argument.